All right, there were lots and lots of comments on the Pressfit is better video. So well over 200 comments. So I wanted to talk a little bit about that. I said it was open for debate, so I'm here to debate that. So first off, we'll go through some of the history of bottom bracket shells. So the original bottom bracket shell was a threaded bottom bracket shell. Now, that was done because the bearings, and I'll show you a picture. So how bottom brackets and crank axles and stuff used to fit on the bike. So basically the cups were adjustable and there were loose balls, and the axle had a race in it as well. So not like today where you've got, typically you've got cartridge bearings. It was a loose ball bearing system, and you used to have to adjust the preload on those bearings. So you had a fixed cup on the drive side, and you had an adjustable cup on the non-drive side. And so what you do is you'd service your brake. And these, when I first started playing around with bikes many years ago, that's what you had. And so, particularly when you were riding in weather that wasn't so great, you'd they weren't sealed as well like the bottom brackets are today. And so you'd have to pull it apart and clean it all out and re-grease it, and then readjust the preload. So what happened, and it was probably around the early 1990s that the whole concept of a cartridge bottom bracket assembly came into play. So that came in because it was much easier from an assembly point of view and from a maintenance point of view. So instead of adjusting bearings and things like that, preload on a loose ball bottom bracket, and having to put the ball bearings in there and all this sort of stuff and grease them, you just had this unit which that would just thread into the shell, and that was it. And when it wore out, you just replace the whole unit. And so that was really the turning point for bottom brackets. And so that was the cartridge bottom brackets that so Shimano really sort of started that. And then there were a number of aftermarket ones with titanium axles, and this was all on square taper. That was the standard as well. So the axles were square, had a square taper on the end, and the cranks would bolt on to that square taper. So it would have been probably mid 1990s. Some of the Klein bikes, which were sort of quite progressive at the time, they played around with a Pressfit system where, and I've actually got one of those axles. It was a square taper axle, 17 mil diameter, solid, basically solid axle. Although it had a hollow for the bolts, and the bearings were pressed into the aluminium shell. It was a direct press. They used C3 clearance bearings to allow for the press fit, and it was line board, and that seemed to work quite well. It was sort of a boutique sort of brand in Klein, but so that was sort of the next iteration, which people started to think about that. And then there was a few other things. A Magic motorcycle came into it, and a few other little systems. But the next sort of really big step was the BB30, and that was where you went with a larger diameter axle, so a 30 millimeter axle, so you could utilize aluminium as an axle instead of steel or titanium. So Having a larger diameter gives you more stiffness, and so you can compensate for the lack of stiffness of aluminium compared to steel, and get the weight down effectively. So that was sort of the BB30, and that had the bearings pressed straight into the shell. So it ran circlips as an internal retainer or locator. So you pressed those bearings into the shell. Now, because it was a thin section bearing, the precision required is very, very high. So the tolerances on that housing to get the right fit needs to be really high. So that's sort of why the problems sort of initiated with these sort of systems, and we'll talk about that a bit more in a minute. But we're just sort of going through the timeline. So then the next sort of big change really was the Shimano Holotech 2 system. So Shimano had their Octolink system, which was an oversized axle effectively, but still in a cartridge type threaded bottom bracket. Then they went to the oversize with the Holotech 2. So we're running a 24mm diameter thin hollow steel axle, but the bearing cups were outboard, so they could get a wider bearing stance, and so get better support of the axle by using wider bearings, and get the weight down, and keep things simple, very easy to assemble, but still based on a threaded shell. So because the limitation was putting a larger axle into that threaded shell, and still being able to run a bearing with a large enough section, so that the balls weren't so small that you didn't have any real load carrying capacity. So in the Octolink system, they moved towards a roller bearing for the radial load, with a very small ball bearing for to locate it laterally. So, but with the Holotech, the system is effectively a cartridge bearing that's pressed into an aluminium threaded cup, which is then inserted into the frame. So moving on from there, carbon frames started becoming more prevalent, and that was sort of, in the mid 2000s. That's sort of when carbon frames really started to take off, and people were sort of thinking, well, why do we need to bond a metal insert into the carbon frame if we're just going to run a Pressfit bearing? So then Shimano, with Giant and Scott and a few other brands, came up with the BB86 or BB92 for the mountain bike, which is a Pressfit type. So plastic cups pressed into directly into the carbon shell. So that was basically, had the same bearing stance as the Holotech 2 with the threaded cups, but much simpler. So the next sort of iteration really, then Trek came out with their BB90 system, where they had a big marketing campaign saying, that the bearings fit straight into the frame. So the bearing seats are molded straight into the frame, which in theory, as I explained in the previous video, if you do that really well, there's no problems with that. But in a production sense, they had problems with that. So After that, you had the Pressfit 30 came into it, sort of around the late 2000s, 2009, something like that. Trying to compensate for the problems that the precision problems of BB30. So by having a plastic housing for the bearings, which had a little bit of give, the theory was that you didn't basically have to make the shell as accurate because the plastic would take up that tolerance. So that was the theory behind that. There were a whole bunch of others sort of coming from that as well. Specialized had their OSBB system. There was the BB386 and then BB Right or B Bright, or however you want to talk about it. And they all had problems of their own, and it all came down to the manufacturing tolerance of the housing. So then the sort of latest incarnation has been the T47, where you get effectively a 46 millimeter internal diameter tube, and you thread a 1 mil pitch thread, so hence T47. So that's basically the same diameter as these Pressfit standards, which were 46 millimeter tube, but with a thread. So, and that's sort of the latest iteration, and I think Trek have moved to that system as of the current range. So the questions are like, why go from a threaded? So we know why threaded was originally. So threaded was originally because the cups needed to be adjusted. So that's why they had threaded. And so because all the bikes were done like that, everyone made their system to fit that system, that configuration, because that's what the bikes were. When a bit more design freedom came into it, people could start thinking, well, what would be a better way to make this system? Like, why are we pressing cups into an aluminium threaded? So why are we pressing bearings into an aluminium threaded cup and then screwing that into the frame? Why don't we just put the bearings straight into the frame? Like every other machine, effectively in the world, every other cartridge bearing application, that's how they do it. As I said in the last video, you don't see on an electric motor that they press a bearing into a cup and then screw that cup into the housing. The bearing goes straight in the frame. So why would you want a bigger shell? So that's what it comes down to. So the bigger shell, there are a number of reasons why you want a bigger shell. So you can run a larger diameter axle, so you can get less weight and more stiffness out of that axle. You can run larger frame tubes. So the diameter of the English threaded shell is, the outside diameter is about 40 millimeters. So 40 millimeters by 68 millimeters. So that sort of gives, it limits how wide you can place your chainstays. So you need to, if you want to run a larger wheel, you need to basically have wider chainstays to get that tire clearance. So that's why the mountain bike, they ran in a threaded shell of 73 mil. They had an extra 5 mil clearance to push those chainstays out a bit more to get more tire clearance. Also, the down tubes were getting bigger and bigger. So particularly with the aluminium frames, if you look at an old steel frame, the down tube, it was 1.25 inch diameter, which was actually less than the bottom bracket shell diameter. But now the bottom brackets are tiny compared to the down tube diameter. So by increasing that the diameter of the bottom bracket shell, gives you a larger interface to connect to your bottom bracket. So it's all about driving weight down and stiffness up. So the stiffness to weight ratio. So larger diameters, thinner walls, etc. will give you that. So now the other reasons are they're easy to manufacture. So if you don't have to machine threads accurately into the shell, it's much easier to manufacture. So you don't need to line bore the frame and have jigs and cutting taps and all these extra steps. So by removing that, you make the frames simpler to make. So, and it can be argued, and I mean, I've said this over and over myself, that the frame manufacturers have effectively, because they're not manufacturing the shells to the tolerance that they really need to get these systems to be reliable, they've actually just passed the problem down the line. So instead of the problem being in the factory where the frame is made, they're just passing the problem down to basically the bike shop mechanic who has to fit the bottom bracket bearings into the frame. So if the tolerances aren't right and the fits aren't right, then it's just not going to work properly. So but that's at the bike shop end, not at the factory end. So yeah, they've passed the buck basically. So so that's sort of a bit of an overview of where we've come from and some of the reasons behind it. I mean, we can talk about this sort of stuff all day, like little details here and there, but that's sort of a basic overview. So what I'll do now, I'll go through some of the questions and we'll talk about that. So let's get to some of these questions. So first up, there's a lot of hate for Pressfit bottom brackets. The passion out there is, Pressfit will die, like all this sort of stuff. Just understand this, that it's not the design as such. It's the poor execution of what is a good design which you're getting upset about. So, the same way, if you had one bad apple, it doesn't mean all the other apples are bad as well. So if it's not made correctly, then it doesn't mean it's a bad design. And look, I'm the first to admit that a good design is easy to make. So really good design is simpler to make, etc. So you're less likely to have problems. A good design eliminates some of those problems. But other sort of real topics. I'm just sort of reading some of the questions here. So I mean, there's so many. I can't possibly answer all the questions. I'd be talking for hours. So yeah, one of the other sort of common themes was that the manufacturers, they know how to do it right, but they just don't care, or they choose not to due to cost and weight and all these sorts of things. There's probably some truth in that. Everything comes down to price. So I'll give you an example. So go and see what the cost is of an SKF machine spindle housing and then see how much you want to spend on a bike, because just so one machine housing, just go get a price on the cheapest SKF machine tool spindle housing, and then see what you want to spend on a bike, because to make a housing really, really well is really expensive. So it comes down to how well do you need to make it. And that was some of the comments as well. And people were saying that, you know, there's some which, like, you can have the same bike, you know, his is quiet, he's had good life out of his bearings and no problems, no creaking, and his mate's got the same bike and it creaks and it does this, and he's replacing bearings all the time. It's like, so, you know, that again, that's a quality control consistency problem. So yeah, I mean, there was a podcast recently with the owner of, it was on cycling tips, the owner of Factor Bikes, Rob, and he was talking when he was contracting to other brands making their carbon frames, that like he quoted them at an additional, I think it was $20 to get the bottom bracket done correctly, in his opinion. To get the bottom, yeah, another additional $20 on the cost of a frame, and they wouldn't go for it. That was too expensive. So yeah, that's what you're dealing with. So the other sort of common one was bonding an aluminium insert into the carbon frame to basically, like Specialized did. They had all the problems with their OSBB with the direct press fit cups, and so then they bonded in aluminium inserts. Now, there's a whole range of issues with that, which if done well, that can solve a problem. If it's not done well, it's going to create more problems. So you need to bond it well, which you need to isolate it from galvanic corrosion, etc. But from a tolerance point of view, if you have a thin-walled aluminium piece, it's potentially just going to take the shape of the housing that it's placed in. So it depends on what's got greater stiffness. So it all comes down to stiffness and being able to maintain shape. So if you put a thin walled aluminium piece into a heavy walled carbon tube, and that carbon tube is out of round, when you locate that aluminium piece in it, that aluminium piece is just going to distort to match the carbon tube. So you can allow for that with adhesive thickness, but then you're going to get variations in the adhesive thickness, and then that can be, you know, create other issues as well. So so it's the sort of thing which in theory sounds like, oh yeah, because you can machine the aluminium, you know, you can do it like that. So you know, you could then do a secondary step where you could just bond in an oversized piece of aluminium and then line bore it and do all that, and you know, yeah. So that would be the sort of preferred way to do it if you're going to do it like that. But you still ideally want, you know, it's all about surface area and bonding area and things like that. So, yeah, and consistencies. And so if the shape of the carbon is changing and the shape of the aluminium is changing also due to coefficients, thermal expansion, etc., things are going to move. So it all comes down to the rigidity of the shell. So we'll talk a bit about, people ask, well, what makes a good shell? So primarily rigidity. So you need it to maintain the shape that it's required to have. So there's no point machining a housing, or grinding a housing to this very, very high tolerance if under load it changes shape. You're defeating the whole point. So it needs to maintain the shape. Now, often, in the effort of trying to save weight, they take all this material out of the bottom bracket shell, and then it loses sufficient stiffness or rigidity to maintain that shape. So you're having basically an independent cup on each side of the frame without a tube sort of locating it. You also then, you don't have anything to take the axial load of the axle. So so these sorts of things just create problems, and it's all in, the ironic thing is, people will go out and get a frame like that's really lightweight because it's got really crappy bottom bracket cups, and really lightweight bottom bracket area. But then to get it to work reliably, you've got to put this other type of bottom bracket shell in, or bottom bracket unit, like a BB Infinite or the Hambini style, where you've got this big solid piece of material that provides the rigidity that's required. So why not just do it in the first place? Like, the net weight is the same. I mean, it's all a bit of a contest on, our frame is lighter than the other frame, So it's just a race to the bottom on who can have the lightest frame but has the poorest performance. It's like, it doesn't make sense. So the other things that make a good bottom bracket shell are obviously the bearing concentricity and the fit. And as I said before, go and price an SKF bearing housing and tell me what that costs and how that works. One of the sort of other interesting discussions or topics was, is it possible to correct the fit of an out of tolerance carbon shell, like with epoxy, or laminating some more carbon in there, or something like that? Theoretically, yes. You'd need an epoxy which has got some very specific properties, which is not that typical, and it needs to go very hard. So typically you won't be able to use a room temperature curing system. You typically need an elevated cure temperature, which is doable. Like you can do that. But there are products. There are products like aerospace products that are basically called a liquid shim, which is meant for those sorts of applications where you have the housing or the flange or whatever you're trying to assemble. You have some clearance in that, and then you apply this liquid shim material, and then when you assemble it or jig it or whatever, it cures in the right position, and then everything's good. So yes, there are some of those sort of options available. It's probably simpler just using a Praxis or a BB Infinite or a Hambini, or a system like that. Which it's probably going to be less mucking around. So yeah, I mean, we'll leave it at that. I've spoken enough. My throat is getting dry. Need a drink of water, and yeah. Any other comments you can add it on this video. It's I think these discussions and the interaction with people is great. It's trying to solve some of these problems. So anyway, hope you have a good day. Hope you learned something, and we'll talk to you again soon. Okay, bye.